On Friday before the break, we defined the difference between an elastic and an inelastic collision. You will almost certainly on your diploma exam coming up in June get a question that asks you to differentiate between an elastic and inelastic collisions. And one of the things that it's going to actually ask you to differentiate, one of the factors that it's going to ask you to differentiate on is momentum. The other one is kinetic energy. We know in an elastic collision, momentum is conserved. We know in an inelastic collision, momentum is conserved. And there's a mistake that a lot of people make. They automatically say elastic momentum is conserved, inelastic momentum is not conserved. Okay, momentum is always conserved if you have an isolated system, and in these cases we're assuming that we do. Okay, so momentum is always conserved in both cases. But what about kinetic energy? That's our other factor here. Is kinetic energy conserved in an elastic collision? Yes, it is. That means that kinetic energy stays the same whenever we have an elastic collision. Is kinetic energy conserved in an inelastic collision? No. It means kinetic energy is lost. We're never going to find in a collision that kinetic energy is gained. There has to be an explosion taking place to gain kinetic energy. And we're not going to talk about elastic and inelastic in the context of an explosion, only collisions. So it'll either stay the same or it'll be lost. It's either elastic or it's inelastic. Now, it's pretty rare that we actually get a truly elastic collision where kinetic energy stays the same. Can anybody give me an example of a situation where I may get a truly elastic collision, Tristan? Good. When you have subatomic particles colliding, it can be truly elastic. Give me an example of a situation that's on a more macroscopic scale where the collision is almost elastic. Sometimes, to the correct number of significant figures, it may show that it is elastic. Yeah, Chad? Sorry? Yeah, pool balls or billiard balls. Why, when you have subatomic particles, do you usually get a truly elastic collision? Why, when you get billiard balls colliding, is it almost elastic, Chad? Okay, good. And in billiard balls, they don't really compress very much, at least not a noticeable amount. So why can't we get any compression? Chad's answer was, in subatomic particles, the particles don't really compress at all. And when we don't have any compression, we don't have any loss of kinetic energy. But why not? Okay, why when you bounce a basketball on the floor do you lose kinetic energy, but when two billiard balls collide, you don't really lose at least a measurable amount of kinetic energy? Yep. Okay, so that explains why it compresses, but it doesn't explain why compressing causes it to lose kinetic energy. Yeah, not quite with, we don't want to go with the impulse thing there. I mean, yeah, that does provide less force on it because it increases stopping temperature.
When the basketball hits the ground, there's a conversion of kinetic energy.
Good. Good. Whenever you have an energy conversion taking place, you learned this in Science 10, right? Whenever we have an energy conversion taking place, we always lose a little bit of energy. When you bounce a basketball, when the basketball collides with the ground, you have a conversion of kinetic to elastic potential and then back to kinetic energy again. Forget about the fall of the basketball. That's a whole other problem. The actual collision involves a conversion of kinetic to elastic potential back to kinetic. In both of those conversions, we lose a little bit of energy. So we can't have as much kinetic energy at the end as we started with. Therefore, it's inelastic. When two billiard balls hit or two subatomic particles hit, then there's not really any conversion taking place because there's no compression. If there's no compression, there's no conversion. If there's no conversion, there's no energy lost. So the final kinetic energy should equal more or less, at least, what the initial kinetic energy is. Good? Okay, if I gave you an example of a collision, let's say two cars collide and they bounce apart. Do we know right now whether that's elastic or inelastic? Sorry? It's elastic? Could it be elastic? Yes, it could be elastic. Although in all likelihood, if two cars collide, it probably won't be elastic. But if they bounce apart, it's possible. Okay? Sometimes it's elastic, sometimes it's inelastic if they bounce apart. What if those two cars collide and they strike each other and they stick together? The metal entangles and they stick together and head off as one object. Do we know whether that's elastic or inelastic? Okay. Good. We know that it's inelastic for sure. We don't need to do a calculation. If the time comes when we do have to do a calculation, what calculation is it that we're going to do? What numerical analysis can we do to determine whether something's elastic or inelastic if we can't determine it based on them sticking together or bouncing apart? What's the whole idea of elastic and inelastic? What has to be conserved? Right. Kinetic energy has to be conserved. Then let's get the initial kinetic energy of all of the objects combined, and we'll get the final kinetic energy as well of all the objects combined. If they're the same, it's elastic. If final is less than initial, then it's inelastic. If final is more than initial, then you made a mistake, right? If final is more than initial, then you made a mistake. So try again. Okay. We have 2 questions on the first set of homework here, page 482, number 1 and 2. Any issues with either of those questions? No? Okay, I want to take a look at number 2 here anyways. Not necessarily completely. If we need to go into more detail, we will, but there's just a couple of things that I want to point out about it here right now. First of all, we have an argon atom colliding with another argon atom, both with the same mass. First one going at 17 meters per second to the right. The second one going at 20 meters per second to the left. I'm circling left there to remind me that it is opposite in direction to the first one. They bounce apart, so we don't know whether it's elastic or inelastic or what it is. If I had to guess on this, though, we could see the answers there is it's elastic. If I had to guess, I would have guessed elastic. Anybody suggest to me why I may have guessed that? Yeah, Caden? They rebound, yeah. Although when 2 things hit each other and bounce apart, it could be elastic or inelastic. In fact, most times it'll still be inelastic. Most times. Why would I guess this one, though, to be elastic? Yep. Yeah, it's not subatomic, right? It's atomic, or it's argon atoms, but it's pretty close, right? They're still pretty small things. Are you going to get a lot of compression there? Maybe a little bit, but to the number of sig figs that we would measure to, then we're probably going to find that the kinetic energy is equal. That's a good point too, actually, which I didn't even notice. The speeds stay the same. The velocities don't, because they rebound, right? But the speeds stay the same, and since the masses and speeds are the same, then kinetic energy should be the same, right? In the end, even when you're looking at that, though, you're somewhere in your head kind of doing a bit of a calculation to say, okay, it's going to stay the same. Okay. All right. Let's set this up here, okay? Let's say that the initial kinetic energy is 1/2 mv squared, 1/2 m1 v1 I squared plus 1/2 m2 v2 I squared. How many people here caught this, that the masses are the same? M1 and M2 are the same, and therefore we can cancel M1 and M2. How many people did that? Okay, if you did, and still got that it was elastic, well, you probably still would get it if it's elastic, but you kind of got lucky on it, because that's wrong. You can't cancel those. Why can't you cancel M1 and M2 there? Why can't you cancel M1 and M2, even if they're the same mass? Okay? Yeah. In order to cancel something, it has to be in every term. Okay, if it's 6.63 times 10 to the minus 26 kilograms here and here, it also has to appear on the left-hand side to cancel it. Now, when you canceled that, you would have gotten a number for your initial kinetic energy, and you would have gotten a number for final kinetic energy that would have been the same number. It just would have been the wrong number, that's all. Does that make sense? If it's a multiple choice question, you would have gotten away with it. If it was a written response, it would have been marked wrong because you made a mistake there. So don't cancel M1 and M2, even if they are the same mass. Now, the next thing that I wanted to point out is the speeds here. What's this one going to be? V1I is what? 17, positive or negative? It's 17 meters per second, positive or negative? Positive 17 meters per second. V2I, 20 meters per second, positive or negative? No, positive 20 meters per second. Why? We're talking about kinetic energy here, and kinetic energy depends upon speed. Both speed and kinetic energy are scalars, not vectors, so we don't include direction. I don't care if it was 20 meters per second at 36 degrees south of west. It doesn't matter. The direction is irrelevant. Just put in the number for speed, not the direction. Does that make sense? Now, having said that, you probably, if you did that, would have gotten lucky there as well, because you would have squared the negative and gotten gotten a positive. But try to stay away from that. Even if you do end up getting the right answer, we don't want to get the right answer because we got lucky. We want to get the right answer because we knew exactly what we were doing. Okay, so don't put in the negative. Don't put in any direction there. Okay, when you calculate the initial kinetic energy and the final kinetic energy to the right number of digits at least, they should be the same, and therefore it's an elastic collision. Is that good? All right, let's take a look at the second set that we had, page 486, number 1 to 11. Seems like forever since we've done this stuff, eh? Any issues with those questions 1 to 11? I want to do number 11. I don't know about the rest of you guys, but I think that's a good one to do. Good one to do because it's a little bit tricky, but it also reviews not only what we did on Friday before the break, elastic and inelastic, but it takes us back to collisions before that as well. Wilson? The one with what? Space shuttle one? Yeah. We got 7, 11. Going once, going twice, 7 and 11 it is. Number 7 says that liftoff, a space shuttle has a mass of 2.04 times 10 to the 6 kilograms. The rocket engines expel 3,700 kilograms of exhaust gas during the first second of liftoff. So that's pretty quick, right? It's a lot of fuel in 1 second. 3,700 kilograms. You can imagine how, I mean, there's a lot of costs involved in running a space shuttle program, a space program in general, but when you're producing 4 tons of exhaust in the first second of liftoff, that's a lot. That's a lot, and that's going to be pretty expensive. Gives the rocket a velocity of 5.7 meters per second. So 0 to 5.7 meters per second in 1 second. That's okay. It just takes 3,700 kilograms of exhaust to do that. What velocity is the exhaust gas leaving the rocket engines? And it's telling us to ignore the change in mass due to the fuel being consumed. In other words, the space shuttle has a mass of 2.04 times 10 to the 6. We're not going to bother subtracting the mass of the fuel that was converted to exhaust gas. Okay, it's not going to really matter there. This question, if we treat it the way we really should, it's much more difficult than any question you've ever done or ever will have to do in Physics 30. This is really a calculus question. It really is. Can anybody explain to me why this is not a straight PI equals PF question? That's the way we're going to treat it, because it's a good approximation. But this is not a perfect PI equals PF question. Anybody see why? What's the issue with this? Right, we've got a rocket, basically, right, a space shuttle that ejects this gas out the back. Space shuttle goes one way, gas goes the other way. That should be PI equals PF, right? And it is, but it's a little bit more complicated than that, sorry? Yes, it doesn't happen at once. The mass of the rocket is constantly going down. The mass of the exhaust is constantly increasing. It's not like one moment the space shuttle and the exhaust are all one, and then the next moment there's 3,700 kilograms of exhaust out the back. There was 1 kilogram of exhaust before you had 2, and then there was 2 before you had 3, and so on and so on. So it's a changing amount. Does that make sense? Because it happens so quickly, though, over 1 second, PI equals PF, the way that we treat these problems, is a pretty good, it's a very, very good approximation. If we were talking about this, though, over 10 seconds or 15 seconds, it wouldn't be a very good approximation at all. Okay, so we'd have to go into a much more detailed analysis, and you'd have to have a lot more calculus in order to do that. All right, let's circle some givens here, okay? We have M1 here. Okay, we have M2. M1 is going to be the mass of the shuttle. M2 is going to be the mass of the gas. The shuttle goes off with a velocity of 5.7. We're going to call that V1I. Sorry, V1F. V1F. What's V1I? The shuttle and the gas are sitting there, right? So it's 0. What are we looking for here? Well, We're looking for the velocity of the exhaust gas, right? V2F. So we're going to say Pi equals Pf, even though we know that we're doing a bit of an approximation here. What is the initial momentum? As the shuttle sits there with the fuel in it, what's the initial momentum? Same as it is when the shuttle is sitting in its hangar in the California Science Center, right, where it's zero. It's got 0 kilograms meters per second of momentum because it's not moving. Afterwards, you've got the shuttle and you've got the exhaust gas. Now they're telling me to ignore the fact that the mass of the shuttle actually decreases a little bit. Doesn't decrease very much compared to its initial mass, so we're just leaving it what its initial mass is. It was up at 5.7. M2 is 3.7 times 10 to the 3, 3,700. And we multiply that by V2F. 2.04 times 5.7, take that over by subtracting, divide it by 3.7 times 10 to the 3. What do we get there? I think it was, I don't know, about 400 meters per second or something, wasn't it? Oh, yeah, I was way off then. 3,100 or negative 3.1 times 10 to the 3 meters per second. Negative because it's going downwards, right? This is a much bigger velocity than the velocity of the shuttle itself, right? Would you expect that? Yeah, sure you would. Because the shuttle is much more massive than the gas. The gas is going to be moving much faster than the shuttle. Right? Question, Wilson? Let's take a look at number 11 now. It says a 220 kilogram bumper car going north at 0.565 hits another bumper car and rebounds to the south. Bumper car B was initially traveling to the south, and after the collision they moved north at 0.395. What's the mass of bumper car B? And determine whether it's elastic or inelastic. Ideally, we'd be able to tell whether it was elastic or inelastic now. Okay, if we could, without doing a calculation, then we would have to see that the two cars, when they hit each other, stuck together. If they bounce apart, it could be either elastic or inelastic. We don't know. Okay, the only way out of doing a calculation is if they stick together, it's inelastic. They don't here. So let's start identifying some givens. That's M1. And the other one is going to be M2. That's what we're trying to find, I guess, isn't it? Mass of bumper car B. This is going to be V1I, the initial velocity of car number 1. This is going to be V1F. It rebounds at 0.482 to the south. This is going to be V2I, and this is going to be V2F. So we have everything here except for M2. That's not usual. Usually we're solving for a velocity, right? Not a mass. See what we can do. M1 V1I plus M2 V2I equals M1 V1F plus M2 V2F. 220 times 0.565 plus M2. What's M2? Oh, we don't know. We're trying to find that. V2I was negative 0.447 because it was to the south, right? V1F, it says, is negative 0.482 to the south. And V2F is 0.395. How many people got this far? Did it bother you when you saw M2 in two places? Let me just do a little aside over here. Let's say 2x plus x equals 4. How do you solve for x there? How do you solve for x? Go on. Take the x out. Okay, yeah, you can do that. Absolutely, you can do that. What's the other way of doing it? Yeah, you don't even have to. It's simple, guys. Don't make it harder than it has to be. 2x plus x is 3x, right? So that's x equal 1.33, whatever. That makes sense, guys? Kevin, your way works. Yeah, absolutely. It's just, it's an extra step, but it's not a big deal. Okay? In the end, all we're doing is combining terms that are the same, right? Combining the x's. Okay, let's change this around a little bit. Let's say that it's 2x plus 4 equals x. Now what are you going to do? Same thing ultimately, right? Is combine the like terms. We can take the 2x over to the other side by subtracting, or we can take the x over here and the 4 over here. It doesn't really matter. Okay, I would probably, since it's only one step, take the 2x over. Okay, it's the same as 4 equals x minus 2x, or 4 is equal to negative x. Make sense? Therefore, x would be equal to negative 4. If we can combine x's, then we can combine m2's in exactly the same way. Let's get these two numbers. Let's multiply those two numbers and get a number 4. Let's do the same thing with this. Okay, those two numbers. There's no m2 beside those, so let's get those two numbers in green, and let's combine them. And then let's do the same thing with this and this. So let's get those, and then let's combine them because they both have m2's after it. Okay, let's do this on the calculator together here. Let's see, 220 times 0.565 equals. Okay, that's 124.3. Now, let's bring over to the left-hand side 220 times 0.482. Why did I add that to the left side? Because it was a negative on the right-hand side. So now on my left-hand side in green, I have 230.34. On the right-hand side in red, well, remember, if 1x and 2x is 3x, and we're going to take this over by adding because it's a negative, then we're going to say 0.395, can't find the 3 there, there we go, 0.395 plus 0.447 gives me 0.842 from 2. All I've done is taken the negative 0.447 m2 over by adding. Gives me 0.842 m2. Let's divide that by 230. Sorry, let's say 230 divided by that, I should say. 230.34 divided by that, 273.6. Everybody get that? Good. Let's round out to 3 digits. We get 274 kilograms. Although we'll keep the unrounded number because we're going to use that in our second question, question B. Elastic or inelastic? Well, EKI is equal to 1/2 m1 v1 I squared plus 1/2 m2 v2 I squared. Oops. Masses cancel here? No, for 2 reasons. 1, because they're not the same mass, and 2, because they don't appear in every term. Have I missed anything there? Is that 0.482 correct? Should it be negative 0.482? No, we're talking about speed, scalar. Okay, don't put in the negative. We get a number there. I'm not sure what it is. We do the same thing for the final kinetic energy, though. We're going to say 1/2 of m1 v1f squared plus 1/2 of m2 v2f squared. Okay, we got the masses. v1f is 0.395. All right. V1f is 0.482. And V2f is 0.395. Don't pay any attention to direction. Okay, get those two numbers. What do we find about EKF? pretty sure you're going to find that it's smaller than EKI. Anybody get that? Anybody find that it was bigger? If you did, you made a mistake. Okay, EKF will not be bigger than EKI. It'll be smaller or the same amount, usually smaller. Good? All right, let's take a look together. We'll just do this one together at one multiple choice question. Number 16, I think it appears on page 14 or 15 of your worksheet booklet. Okay, this one says, number 16 says, which of the following statements best describes inelastic collision shown above? Okay, forget about the options right now. We don't care about those right now. Let's just set up the question itself. I told you guys at the beginning of class when we went through a review that you are almost certain to see a question on your diploma exam that asks you to differentiate between elastic and inelastic collision based upon two things. Okay, based upon kinetic energy and based upon momentum. The answer is always the same to whatever that question is, however it's phrased, whatever the context is. Momentum is conserved in both. Kinetic energy is conserved in an elastic, but not in inelastic. Okay, so it doesn't matter whether we're talking about two cars or two billiard balls or two whatevers. Okay, remember that. Momentum is always conserved. Kinetic energy is conserved in an elastic collision. Okay, we know that. Now let's look at our options and see which one best describes inelastic collisions. Momentum is conserved. Kinetic energy is not conserved. Which one best fits with that? We may have to change the wording a little bit, but in the end, which one matches up with that? Kinetic energy is lost. Momentum stays the same. It would be B. Yeah, it'd be B. Yeah. Because I mean, strictly speaking, any collision can be an isolated system if you look at just before and just after, immediately before and immediately after. Now, the collision itself, okay, just before the collision, just after the collision, if it's not isolated, it's pretty darn close to isolated. Here's what a lot of people will say. They'll say that kinetic energy is lost because it's inelastic. They remember that. But they also, for whatever reason, think when it's inelastic that momentum is also lost. It's not. Okay, momentum stays the same as long as it's isolated, as Claire was alluding to there. How many people got B for that?